Stripping down science. The Naked Scientists.
Hello, and welcome to this very special Best of the Naked Scientists with me, Meera Senthilingam.
And me, Ben Valsler. Chris is still away, so we're back with more of the best bits from the last series. Coming up on today's show, we discover a potential new measurement for risk.
I would say that the risk posed by a curtain over 1 year, being substantial as we now know, should be the unit of measurement. So one curtain would be that amount of risk.
Find out about some clever birds.
Some members of the crow family, one in particular, the New Caledonian crow, actually makes tools. So this sort of puts it on a par with the chimpanzees.
And what on earth makes Dave Ansell sound like this?
Well, I hope that makes sense to everyone, and everyone has a great evening.
That and lots more of the best naked bits to look forward to on today's show.
The Naked Scientists podcast, powered by UK Fast, the UK's best hosting provider, on the web at ukfast.net.
Now time for a roundup of some of the exciting news that Chris and co have stripped down for your listening pleasure.
Now, kicking off with an exciting story this week, because scientists down in the Medical College of Georgia have responded to what can be described as anecdotal reports of people coming into the emergency room, the casualty department, having been bitten by a kind of tarantula. And the name of this spider is Phoneutria nigriventa. It's a fairly big tarantula, but when people were bitten by it, as well as the usual symptoms of being bitten by something poisonous, in other words, you get pain and swelling, the male people who came in complained that they had an erection that wouldn't go away. And why doctors are very excited about this is because this suggests that there's something in the venom of that spider which acts on blood vessels. So as well as possibly holding the clue and the solution to solving the problem of impotence, it might also give us some clues as to new ways to tackle the problem of blood pressure and blood vessel-related diseases. Now, the work's been done by somebody called Kenya Pedroza Nunes, who's actually at the Medical College of Georgia. And what they did was to take samples of the venom from this spider and then analyse it chemical by injecting these chemicals into male rats until they found one, it's a small protein, which they've dubbed TX26. And that was the one which reproduced the same effects as you see in humans. And then they analysed how it works, and it's very different to any other class of drugs that we have to try and control blood pressure and make blood vessels do things. What this one does is it acts on a substance called nitric oxide, and nitric oxide is a small chemical and it dilates blood vessels. So when you put this into a person or a rat, then it goes to all the blood vessel walls and it causes them to make lots of this nitric oxide, which causes blood vessels to open up. So the researchers are really excited because this opens up a new avenue and a new target for trying to make drugs that can control vascular disorders.
Wasn't Viagra found by mistake in a similar sort of way?
Yes, they were looking for a treatment for trying to deal with the problem of high blood pressure and open up blood vessels. And lots of the people who were entered into the trial complained of the same symptom of these people who were being bitten by spiders. And they realised that Viagra was much better at actually curing the problem of impotence than curing the problem of high blood pressure. So it got marketed as an anti-impotence drug. And hasn't it done well? I mean, it makes Pfizer, who make it, I think in the order of the latest figures, $434 million every year.
So don't be too surprised if your inbox gets full of spam emails offering the services of tarantulas.
I always thought that Viagra, being those little sort of triangular pills, looked a bit too much like the breath mints that you get in packets at motorway service stations.
I can't say I know what Viagra looks like, Ben.
Well, I'm only basing this on what I've seen in my inbox and those emails that get filtered.
What you've seen in your inbox.
Anyway, on to the next bit of news, which is why I mentioned it.
Have you ever noticed that when you suck on a mint and then you take a deep breath, and I know all about this because I've been sucking one or two cough lozenge type things this week, your mouth feels very, very cold. Have you noticed that?
Yeah, I love mints.
But why does that happen?
It's something to do with menthol.
Yeah, it is. And for a long time, scientists have suspected that menthol was something to do with this, but they didn't exactly know how. And this week, there's a paper in the journal Nature by a researcher from the University of California, San Francisco, called David Julius, and they've discovered the reason why this happens. And it's all down to what's called an ion channel, TRPM8, that's the name of it. It sits on the surface of a very special family of nerve fibres called cold-sensitive nerve fibres. And when these nerve fibres are exposed to low temperatures, this TRPM8, which is a little protein, changes shape and it changes the activity or the excitability of the nerve fibres, and it makes them become much more excitable than they were before, and so that's how you detect when the temperature is falling. And what they did was to remove this gene from mice, and they found that the mice who lacked this gene were quite happy sitting on a cold surface or a warm surface when they gave them a choice. And normally, if you give mice a choice between a warm surface and a cold surface, then they will always choose the warm one, because little animals lose heat very, very quickly.
And what's this got to do with mints? Did they feed them mints?
Well, metaphorically they did, because you can stimulate this pore with menthol, the same thing as cold temperature and menthol. They both work the same way. So what the menthol is doing is it makes this shape change in the protein happen automatically with the menthol without any reduction in temperature. So it fools your mouth into thinking it's colder than it really is. And so that's when you see this cold breath phenomenon. When you're taking in a breath of air, the nerves are firing off faster than they would do normally. But that makes you think your mouth's colder than it really is.
Absolutely fascinating.
Now, Kat, what's your memory like?
Oh, sorry.
I've forgotten already.
I forgot where I am. Goldfish-like in my case.
Well, maybe you wish you were at the University of Lübeck, because there's a researcher there called Jan Bonn who's found out literally how to make I suppose the best way of putting this is a thinking cap, because he recruited some groups of medical students and gave them some rather bizarre pairings of words to remember, like red and Byzantine, word combinations you wouldn't normally associate with each other, and asked them to remember as many as they possibly could and tested their ability to recall them afterwards. And then, in a second trial, they put electrodes on their heads, and when they went to sleep, they stimulated their brains with what's called slow-wave oscillation. Now, when you first fall asleep or drop off, your brain has these very characteristic brain waves, which are this slowly undulating waves. And scientists originally thought that they were really just what's called an epiphenomenon, a sort of side effect of the brain going about its business of falling asleep. But actually, when these students were retested after they had this brain stimulation, they performed significantly better at remembering these bizarre facts they'd been asked to remember. And what the researchers now think is that during this slow wave sleep, a part of the brain called the hippocampus, which is involved in laying down fresh memories, when you go to sleep, the hippocampus replays the experiences of the day, and during this replay, you get consolidation, the conversion of those short-term memories into long-term interconnections between nerve fibres that give you your long-term memories. And this sort of slow-wave sleep seems to be very important in doing that, and so by encouraging more of it, you make your memory better.
I wonder if it can help me remember what I've done with my keys.
You said to me, Kat, you refused one of my wife's delicious cakes that she's made today on the grounds that you're dieting or something.
Well, I've given up. I've given up eating cakes for some reason.
So, are you on the skimmed milk then as well?
Yes.
Okay, because this might be interesting to you, because there's a cow which has been flushed out from New Zealand. It's actually been published this week by Via Lactea, which is a biotech company in New Zealand, and they found this cow which they've christened Marge in 2001, and Marge naturally makes milk which is skimmed. It's very low fat, and the reason they called it Marge, the cow that is because when you make butter from Marge's milk, it spreads easily straight from the fridge, even at low temperatures, and the reason is because the milk contains very little saturated fat. It's only got 1% fat in it compared with 3.5% fat that you'd normally find in milk. And the milk's also good from the point of view that it's very rich in omega-3 fatty acids, which we know are important for colour vision and possibly cognition. There's a number of anecdotal studies that if you give this to young people, you can boost their reading power and brain power.
Apparently.
And things. And people who eat a lot of cod liver oil and oily fish seem to have better preserved intellect into old age, possibly. But anyway, what's really interesting is that it's not just an isolated one-off cow, because the genetic trait, although they haven't tracked it down, it's dominant, which means that all the calves that they've managed to breed from this cow also have the same trait. And so there's a guy called Russell Snell, who's the scientific advisor to this company, has said that by 2011 they're going to have a whole herd of these low-fat cows which they'll be able to milk, and you'll have literally skim low-fat healthy milk direct from the udder.
Oh, brilliant. I wish they'd make low-fat cheese.
Low-fat chocolate would be probably more of a breakthrough, I think.
That definitely would.
The benefits of milking Marge could be more than just spreading from the fridge, as Chris explained when answering a question from Sheila.
Question for you. Does drinking too much milk, i.e. calcium, reduce your physical endurance or stamina?
I can think it probably would, because if you drink tons of milk, it will make you quite fat. And if you get too fat, then, of course, you're carrying enormous amounts of weight and therefore burning off lots of calories. And that's going to reduce your endurance, isn't it? What are the side effects of drinking lots of milk? Well, if you drink milk that isn't skimmed, it's got lots and lots of fat in it. So having lots and lots of fat isn't good for you because of the calories, but also because it furs up your blood vessels. Milk's also very rich in calcium, which means in people who are prone to stones, like kidney stones, if you don't drink, if you have too high calcium, you can deposit that in your kidneys and get kidney stones. And the other side effect of milk that not many people know is if you have irritation to the stomach lining, and you're at risk of getting, say, stomach ulcers, calcium is used as a sort of a co-signal by the wall of the stomach to produce acid. So if you have calcium levels going up in the blood, you make more acid. Now, some people, when they have a bit of a dodgy stomach, they'll think, I'll drink some milk to settle my stomach. Now, when you first do that, your stomach feels a lot happier because what you've done is to give the acid in your stomach something other than the wall of your stomach to eat. So as a result, then you feel better. But then the calcium gets absorbed, goes into the bloodstream, increases the amount of acid your stomach wants to make, and so you get a vicious cycle and the whole thing comes back together again. So, not good.
Still to come, we've got Joel Veitch proposing a new unit for the measurement of risk, and we pick out some of our favourite kitchen science experiments.
The Naked Scientists, supported by the Wellcome Trust.
This is a special edition of The Naked Scientists with Ben Valsler and Mira Senthilingam. We're looking back through some of the best bits from the last series.
Still to come, we hear from Jonathan Shanklin about the current state of the ozone hole he discovered 30 years ago, and why some birds could be as clever as chimps. Now though, have you ever thought about how to measure risk? Should we say something is as dangerous as crossing the road, or should we compare it to having a barbecue on a petrol station forecourt? Joel Veitch from the website rathergood.com, better known for its animated music videos than its science, has been studying the stats and come up with his suggestion.
Well, yeah, I did notice that people were starting to talk about nanohazards and whether there should be warning signs for them, that sort of thing. And it struck me that really no one had really defined what a nanohazard actually is, because it turns out there is no SI unit for the measurement of hazard. So an SI unit is like a metre is an SI unit of length, for example.
So what are you proposing?
Well, I had to look into the statistics, because without statistics, science is nothing. And I thought, well, really what we should do is we should find something which poses a decent amount of hazard to a large number of people. So having looked through, I realised that curtains, which are something that, of course, most people are exposed to on an almost daily basis.
What sort of curtains did you have in mind, then?
Actually, it's non-specific. It's any kind of curtain. So if you have curtains in the home, then this is a hazard which applies to you, obviously. Looking at the statistics for 2002, they actually caused 4,080 injuries in 1 year.
So what, people closing them, opening them? This is the classic joke when someone goes to the doctor and says, doctor, I feel like a pair of curtains. The doctor says, pull yourself together. I mean, this is what I'd like to say to whoever did this survey.
It doesn't specify the kinds of injuries. One can only guess, but it does specify an awful lot of other things which can cause injuries, and I hate to imagine what those injuries might be.
Well, I had a look at the Royal Society for the Prevention of Accidents' website, in which they publish some of these details. And not surprisingly, building and DIY causes about 1 million accidents a year nationally. But then I had to look further down. I mean, looking at this, bread bins are absolutely lethal. 185 people a year are injuring themselves on bread bins. We need some kind of warning and regulation on bread bins.
It's true. We should. And interestingly, having another look through there, you'll see that some things which you would have thought would be inherently evil are in fact quite benign.
Well, compasses and dividers. I mean, a compass, nice big pointy spikes in it, the kind of thing teachers would love to ban from classrooms. 0 accidents last year. We need people injuring themselves with these things, so we get them banned.
It's right. And a mincer, 1 accident with a mincer, and again with a mangle.
Well, paper clips apparently caused 62 injuries last year, which is devastating. Maybe we should ban those.
Maybe we should. I've never found them terrifying myself, but,
But returning to the sort of curtain issue,
yes.
What did you propose that we should do in terms of coming up with some kind of nomenclature and unit of risk then?
Well, yeah, assuming that we actually need a unit for the measurement of hazardicity, or risk, as we could say, I would say that the risk posed by a curtain over 1 year, being substantial as we now know, should be the unit of measurement. So 1 curtain would be that amount of risk. And then we could measure the risk posed by other things in relation to their hazardicity compared to curtains.
So building and DIY would be like a mega curtain?
Yeah, or possibly even a giga curtain. Depending on...
So vacuum cleaners, which cause 10,000 injuries every year, I perish the thought, why? If people didn't hoover naked, I suppose it wouldn't happen. But that would be, on your scale then, that would be roughly 2 times 4,000, that would be 2 curtains of risk.
Yeah, just over 2 curtains, yeah.
Okay, so what's a really small risk then?
Well, one good example would be an artist's brush.
How harmful is that then?
Well, in fact, that is how sensitive the data set is, and by that I mean the the data we've got only goes down to 1 accident per year in the UK, or in fact 21, because it's only 1 in 21 people covered by the survey. So there's only 60 million people in the country. So that means that you can't have, literally every possible hazard, because if there's no one injured by something in this country,
you can't quantify.
Then it doesn't it doesn't figure on the stats. So we can go down to, for example, an airbed poses a risk of exactly 1 centicurtain, pretty much. So 1/100th as dangerous.
How do you injure yourself with an airbed? I mean,
well, I presume maybe some kind of bouncing, or I have actually gone a bit faint trying to inflate them myself from time to time, so I can see how that could result in a falling over.
Right, so what do you think the chances of Downing Street embracing your proposals and us having a warning system based on the curtain level of risk?
I think that really depends on how much of a fuss we kick up, really, doesn't it?
Are you going to take this to the House of Commons?
Well, we should. I mean, it occurs to me we have a new Premier coming in, don't we? So maybe we should give him the opportunity
Well, they're really quite... This government really quite into regulations and things, aren't they? I also noticed that on ROSPA's website that a real hotspot for accidents and damage are in cemeteries, which I think is quite appropriate, really, isn't it? You're in the right place to injure yourself, because then if it's really fatal, you can just fall into a hole and that's that. But
yeah, I suppose so, yeah.
Thank you very much, Joe. It's been great having you on the programme.
Oh, thank you.
Next, a story about hiding food, building tools and planning for the future. For birds, that is. Chris spoke to Nikki Clayton.
I work on a number of birds. They're all members of the crow family, which includes the ravens and magpies and jays. And the ones I work on are jays, rooks and jackdaws.
But why do you want to study these birds? I mean, obviously it's important to study all kinds of species, but why are you particularly interested in this family of animals?
Well, these birds are particularly clever. We think of them as the feathered Einsteins, if you like, or the feathered apes of the bird world. They're the really clever ones. They have huge brains for their body size, and there are all kinds of examples of just how clever they are.
One of the things that you did recently was to see how good they were at planning for a rainy day. So tell us about that.
Well, these birds hide food for the future, and we call it caching behaviour, simply from the French, to hide. And what we were interested in was the extent to which they could actually plan, because obviously many animals, squirrels hide food for the future, all kinds of animals hibernate or migrate. So many animals have forward-looking behaviour, but there's a difference between just having a simple forward-looking behaviour that might be triggered by a seasonal cue or be entirely inborn, and actual planning, which requires some kind of thinking or forethought.
So how do you know they're actually doing that?
So what we did was we asked whether they could plan for tomorrow's breakfast. And this is an experiment that was actually done by 2 of my PhD students. It was led by Caroline Raby and with much help from Dean Alexis and a member of my department as well, Tony Dickinson. So credit must go to the 3 of them as well as to me. What we did was to ask whether they could plan for tomorrow's breakfast. So we taught them that there were a suite of rooms that they could visit during the day.
Like a bird motel or something?
That's right, a bird motel with a suite of 3 rooms. And in the evening, they went to bed as normal and go to sleep in the dark, just as all birds do. And when they woke up in the morning, they found themselves in one of 2 motel rooms. And on some days, they found themselves in motel room 1. They woke up hungry and breakfast was served, no problem. But on other days, they found themselves in motel 2. Unlucky, they woke up hungry as usual, but there was no breakfast.
I've stayed in a few motels like that.
Absolutely. No names, though. And then all of a sudden, we gave them an unexpected test. Suddenly, in the evening, we gave them the opportunity to hide food as well as eat it. And lo and behold, all the birds put the vast majority of the food in the motel 2 where breakfast wasn't served.
So, in other words, they knew that they'd been hungry there in the past, and so they were relying on this past experience, this past memory, to plan for tomorrow, because they may be in motel 2 and have no food.
Exactly. So the trick of the question is that they hadn't been trained to hide food in either of these rooms. It was a totally novel, unexpected question, and they'd used their past experience about which rooms served breakfast in the morning and which didn't to solve a potential problem. They didn't know where they'd be in the morning, so just in case, put the food in the room where breakfast
Why do they have this trait? Because you can see why we might do that, because we're a bit more complex than they are, but what benefit does it serve this family of birds to have this ability?
Well, it's a very interesting question from a number of levels. My husband, Dr. Nathan Emery, and I have suggested that intelligence has evolved independently in two very different groups of animals, the apes, which obviously includes us, and members of the crow family. Why? Well, we've suggested that it's because actually in the wild they have similar problems to solve. They evolved at about the same time, about 5 million years ago, so about the same time as the apes. And they're highly social. And one of the major theories, theory formulated by Nicholas Humphrey, is that actually the reason why we and other apes are so intelligent is because we live complex social lives. Not just being in a big group, but basically having to keep track of who does what to you and when, and being able to sort of network and do politics. And the argument is that that's exactly the same kinds of problems that members of the crow family solve.
But they don't have people like John Prescott, though, hopefully.
Well, I don't know what the Scrubjay equivalent of that is.
I think one of the most fascinating things that's come out of bird research recently is that they use tools. Tell us a bit more about tool use in birds.
Well, I guess one thing is, why do you need to use a tool if you've got a beak? Well, your beak can only go in so far. So just in the same way as you might have a problem with hands, that if there's a small hole, you can't get your hand in there, it may also be that the hole is sufficiently small or deep that the food is out of beak's reach, and that's when you would need a tool. But I think the most remarkable thing is that some members of the crow family, one in particular, the New Caledonian crow, which, surprise, surprise, lives in New Caledonia, actually makes tools. So this sort of puts it on a par with the chimpanzees. They don't just use tools, they actually manufacture them, and they make different types of tools for different purposes.
And just to finish off, Nikki, is there any clue given to us, if you look at the animal's brain, why these birds have these spectacular abilities compared with other animals that don't perform like this?
Well, it's very interesting because if you look at the relative brain size, so that takes into account body size. After all, it stands to reason that bigger bodies have bigger everything, including bigger brains, and hence why the whales have such big brains. But if you look at it in relation to body size, then obviously we have the biggest relative brain. But if you look at the next ones down, it's the cetaceans, or the dolphins, but it's also the apes within the mammals, and in the birds it's two groups, it's the crows and it's the parrots. And if you look at where the enlargement is in the brain, just as in apes the enlargement is in the neocortex, well, the same is true of the crows. The enlargement is in the avian neocortical area. So it seems to be even in the same part of the brain that is enlarged.
That was Nikki Clayton from the University of Cambridge.
Now, though, we're looking back on one of your favourite kitchen science experiments, where Ben and Dave explored an unusual property of rice.
Hello, welcome to Kitchen Science. I'm in King Edward VI Grammar School today in Chelmsford, and I'm here with David.
Hi.
And I'm also here with Stephen.
Hello.
And, of course, I'm here with Dave Ansell.
Hi there.
Today, we're going to be looking at what Dave's called jammy rice. Now, I can see that he's got a bowl full of basmati rice. He's got a big, sharp knife, which obviously you must be careful with. But he's also got an empty jam jar. Now, Dave, what on earth are we doing with these?
OK, first of all, you want to fill the jar right up with basmati rice. So, Stephen, if you'd like to do that, you might want a piece of paper to act as a funnel.
Dave's now going to roll up a piece of paper to act as a funnel, and Stephen here is going to pour all the basmati rice into the jar.
Possibly not quite all of it, otherwise we'll make a horrible mess. That's probably plenty.
How much rice do we actually need in the jar, Dave? How full should it be?
The jar should be as full as you can get it. So now, Davik, if you like, take the knife, put it into the jar of rice. I just want you to put it all the way down and just wobble it gently.
So, David, what does that feel like, putting the knife in the jar? Is it easy to go in?
Yeah, it's very easy to go in. You can kind of feel the teeny vibrations of the rice, and then it feels cool.
Well, I can see from here that the knife went in really easily, Dave. Is that what we should expect?
Yeah, that's what you'd expect. It's just rice, isn't it? OK, so now what we want you to do is just wobble that knife and keep wobbling it.
OK, David's wobbling the knife back and forth. We can see the rice sort of shifting around it.
Do you notice anything happening to the rice, the level of the rice in the jar, David?
Is it going down?
Level might go down a bit, so what you want to do is slowly top it up with a little bit more rice, keep it at the top and keep wobbling, and then every now and again I want you to take the knife out and push it right to the bottom, and then try and take it out again. Keep going for about 4 or 5 minutes and see if anything weird happens.
And now we're going to see what's a bit unusual about this. So, Dave?
Okay, so what we're going to do is I want you to take the knife out gently, turn it round maybe by 90 degrees, and then push it in gently all the way to the bottom.
Is that easy to do?
That's actually quite hard to do.
All the way to the bottom, really push. Really push. Okay. Now what I want you to do is just let go of the jar and just gently pick it up by the knife.
The rice has actually lifted the jar.
It looks like a jam jar sticking off the end of a knife.
Would you expect that to happen?
No, you wouldn't, but because it's kind of like a knife, and the rice is all loose. So how can it pick a jar up?
So Dave, he's got a very good point. A knife is a nice big thin shape going through lots of little granules. That shouldn't grip on, surely.
The reason why you can pull a knife into and out of rice very easily normally is that there's lots of gaps in between the rice grains. So when you put the knife in, the rice grains can move out of the way very easily. There's no forces involved, so it will just slide in and out gently.
So the rice grains almost act like a fluid, like water. So they move out of the way easily. You can easily push a knife in and out.
Yeah, exactly. Now, when you shake it for all that time, the rice grains are slowly falling into all the gaps between the other rice grains, till eventually there's nowhere for them to move to. So when you push the knife in, the rice grains just squash into each other and jam into each other.
So now, after all the shaking, the rice is acting like a solid that you can push a knife actually into rather than just through.
Yeah, because although there's nothing sticking the rice grains together, there's nowhere for them to move. So they just push into each other and friction holds them together and they act like a solid.
Fantastic. Well, hopefully you will have found that at home and you'll be waving a jam jar full of rice around now. I hope you enjoy it for your dinner. But that's all for Kitchen Science and Kegs in Chelmsford. And of course, it's goodbye from Dave Ansell.
Goodbye.
It's goodbye from me, and it's goodbye from the boys.
Goodbye.
We know how much you enjoy our kitchen science experiment, so we've decided to be nice to you and give you our most popular one later in the show.
Laying the facts bare, The Naked Scientists.
You're listening to a very special edition of The Naked Scientists with Meera Senthilingam and Ben Valsler, looking back over the last series and exploring our best naked bit. Of science, that is.
Earlier this year, we had Jonathan Shanklin in the studio. He's from the British Antarctic Survey and was on the team that discovered the hole in our ozone layer.
OK, the ozone layer is high up in the atmosphere from about 10 to maybe 30 kilometres. And if you brought all the ozone in that layer down to the surface, we'd have just 3 millimetres of pure ozone gas. But that 3 millimetres is actually spread through maybe 20 kilometres of atmosphere. So even in the ozone layer, there's not much ozone.
So it's very thin, isn't it?
It is very thin. And the worry that we have for the Antarctic is that during the Antarctic spring, we have a hole in the ozone layer.
How did you actually discover that hole was there? What were you doing at the time that led you to make that finding?
We were actually making routine measurements of ozone. They started in the International Geophysical Year, 1957-58. And we'd been making them ever since. And really, the discovery was looking not to show that there was anything wrong with the ozone layer. We were trying to show that it was OK and that spray cans weren't destroying it, Concorde wasn't destroying it. And we spotted that during the Antarctic spring, ozone levels were dropping. And we followed that up, found that it was a systematic change, so that it was different each year, getting lower and lower. And then that was published in Nature. And the Americans went back to their satellite data and said, oh, whoops, yes, you're right, we missed it.
Why spring? Because you've mentioned that twice. You said every spring this is happening. What's the significance of the season?
The significance of spring is really why it's over Antarctica, and it's to do with the temperature high in the atmosphere. Once you get up to maybe 14 to 20 kilometres, temperatures get below minus 80 Celsius. And at that sort of temperature, you get clouds actually forming in the ozone layer. Now, chemical reactions can go on the surface of those clouds that convert the chlorine and indeed bromine from halons into an active form, which is basically chlorine monoxide or bromine monoxide. And then when the sun comes back in the Antarctic spring, you get very efficient catalytic cycles that convert ozone back into oxygen. So oxygen has 2 atoms of oxygen, ozone has 3 atoms, and we get about 1% a day being converted back to oxygen.
So what's the significance of the spray cans and things like that? How does that actually contribute? Right, and also, why is it just Antarctica? Why not the North Pole?
The spray cans used to be powered by chlorofluorocarbon as a propellant, and it was also found in upholstery foams, in plastic cartons, and a whole host of exciting uses. And they were mostly released in the Northern Hemisphere. but the process of diffusion means that these get well mixed throughout the atmosphere. Roughly speaking, the concentration of CFCs at the South Pole and the North Pole are exactly the same, but what is different is the temperature. Over the Antarctic, it's every winter cold enough to form these stratospheric clouds high in the atmosphere. But for the Arctic, it's only exceptionally cold winters just due to the circulation in the atmosphere. By and large, the northern hemisphere circulation is more complex, the atmosphere is better mixed, it's about 10 degrees warmer, so these clouds are quite rare. But they have been seen over Cambridge.
So why doesn't the ozone from elsewhere in the atmosphere just sort of flow into Antarctica and replace the deficit, the hole?
Essentially it can't. During the Antarctic winter you get a very strong circumpolar circulation called the polar vortex, and that effectively acts as a barrier. It stops the air mixing from outside the Antarctic into the Antarctic. And so what happens is during the spring you get a build-up of ozone-rich air around the Antarctic. In the middle you get very low levels of ozone, and that's the ozone hole.
I'd just like to backtrack a bit and ask, why is the ozone layer so important? Does it really matter if it's vanished? Can't we just, take the ozone from down at street level and shove it back up there?
It does matter if it disappears, and what happens is that more ultraviolet light from the sun can get through to the surface when there's less ozone. And this UV light can trigger skin cancers, cataracts, genetic damage in microorganisms. So it's not very good for us to have too much UV. And, for example, when we have the ozone hole in the Antarctic, you can get burnt in 5 minutes if you don't put on factor 30 sunblock.
Wow. And how is it actually linked into global warming, which is something we're becoming increasingly aware of?
It's quite a complex thing. The ozone hole is actually completely separate in many ways from global warming, but global warming actually makes the ozone hole worse. And that's because the greenhouse gases act a bit like a blanket. The surface of the Earth is heating up, but in the ozone layer it's getting colder. And the fact that it's getting colder means that more of those clouds can form, more ozone destruction, gets colder still, and it's a positive feedback cycle.
Have the mechanisms we've put in place to try to limit the use of the agents, the CFCs we think are responsible, actually worked? Is the hole shrinking?
There's a big international treaty called the Montreal Protocol, and all bar one of the world's countries actually signed up to the basic thing. So that's really good news, very effective. And the amounts of these ozone-damaging chemicals in the atmosphere are actually going down. So we're definitely getting there with this one. But it is a symptom and not a thing in itself. And unless we tackle the basic level of what's causing many of these environmental problems, things can only get worse.
And just to finish off, Jonathan, just to crystallise this in people's minds, how big is that hole over Antarctica?
The Antarctic is 50 times the size of the UK. The ozone hole is bigger than that. Not by much, but it gives you a bit of an idea of the scale of the thing.
So 50 times our own nation. It's quite a sobering thought, isn't it?
It is, and something that we created off our own bat.
In actually quite a short space of time.
As little as 10 years, and it shows you how fragile our atmosphere is and how much care we need to take in case something similar happens in the future.
That was Jonathan Shanklin updating Chris on the state of our atmosphere.
Fancy listening to The Naked Scientists in your bed, on your way to work, or even at work? Why not subscribe to our podcast? For more information, visit nakedscientist.com/podcast.
Have you ever heard the urban myth that a duck's quack won't echo? Or have you wondered what the world's largest whoopee cushion would sound like? Well, these were some of the topics discussed by Trevor Cox when he came in for a chat with Chris last year.
And we're joined now from the University of Salford, whoopee cushion man Trevor Cox. Hi, Trevor.
Hi there.
Thank you for joining us. Now, let's get that out of the way to start with. I mean, why have you made the world's biggest whoopee cushion?
Well, a couple of weeks back I presented a science show at the Royal Albert Hall. Over the two shows we presented to 5,000 kids a piece of science to try and make them interested in acoustics in general and science and broader. And the whole thing was called Beautiful Music, Horrible Sounds. And a whoopee cushion actually behaves rather like a musical instrument, so it was an excuse to make a giant whoopee cushion.
When you say it plays like a musical instrument, you have to explain that a little bit more. It doesn't sound musical in the sort of Beethoven-type definition.
No, it probably doesn't. But the mouthpieces of wind instruments, such as trumpets and, well, your vocal cords, actually all behave using the same science as a whoopee cushion, which is the Bernoulli effect. So we were talking about the Bernoulli effect with the kids, and we needed something big and impressive, because this show was at the Royal Albert Hall, so every prop had to be massive. So we built the biggest whoopee cushion in the world.
Now, Trevor, your research is about the science of acoustics, and you talk about big halls and things. So tell us a little bit about how big halls can be built better to render sound, and also what happens when you play sounds in certain environments.
Well, if you think about playing sound outside, the sound is rather dry. You might have been to a classical concert where you have your picnic and have the fireworks going off, and you get a rather dry sound because all you get is what's coming basically from the orchestra. And then when you go indoors, what you get is all the reflections from the walls and the ceiling and the floor, and that enriches the sound. It gives you a much richer experience. And I suppose the most obvious effect is some reverberance, the sort of thing you can hear in cathedrals as the sound echoes around.
Now, you were kind enough to send me, actually, a bit of sample of that, so I can try and play you. Talk us what we're expecting to hear, first of all, from this one with the reverberation on it.
Well, this is actually played in a hall, and it's a bit of Tchaikovsky's Fourth, and you should hear quite a rich sound, as you would normally expect from a concert.
OK, let's go for it. Sounds good.
OK, and the other piece you've got is actually played outside the hall. You can imagine it being played outside on a snowy day. There's no reflections at all. It was actually done in a special chamber called an anechoic chamber. And you'll notice it's very, very dry. This is the sort of sound you get from outdoor concerts.
Sounds totally different, doesn't it? I mean, I suppose it goes without saying that the environment makes the concert, I suppose, doesn't it?
Well, it's part of it. I mean, of course, the musicians are probably a most important part, and there's other things like being able to get to the seat without getting wet as you walk from the car park is all very important, and the seat's comfortable.
My sister used to be a tour guide at the Albert Hall, and now they have all those little mushrooms in the ceiling, don't they? And she said that they were put in because the echo was so incredible that a review of a concert in the Albert Hall when it was first built said, "This represents the best value for money, as you can hear two concerts, one 3 seconds after the other." What do those kind of mushrooms and baffles do?
Well, if you're not familiar with the Albert Hall, what it is, it's got a great big dome on the ceiling, and this focus sound, a bit like a concave mirror you might use for shaving. And so what you get is you get really strong reflections off these domes into certain places in the audience. So, and it's so big, the delays are so long, you literally hear multiple sounds. You can hear the trumpets more than once. You can hear people talking more than once. And the idea of the mushrooms, they hang down below the dome, so you can't really see the dome when you're in Albert Hall very well. And they just stop the sound getting into the dome and shorten reflection paths, so it reduced the echo problem.
We've also had a question in here from Nick in Arizona, and he says, is it true that sound travels farther in cold weather rather than in warm weather? And how does this work?
Well, the speed of sound does depend on temperature, and it is slower at colder temperatures.
So it would sound different then?
Yeah, it does. I mean, deep down, sound is the vibration of molecules, and if you've got a lower temperature, those molecules are presumably just vibrating a bit slower.
Trevor, I've got a question here which has been sent in by Nat Bletter, who sent it on email, and he says, why is it that when you're in a car going by a bunch of other parked cars all in a long row, you hear a swoosh for each car as you pass? Is it the gap in between the car filled with air that interacts with the turbulence made by the moving car that makes you hear this?
My best guess would be that's quite a good guess. I have actually no idea would be the honest answer, but it will be some sort of turbulence effect. And we're familiar with turbulence making noise. I mean, that's how things like recorders work. But you also get that whooshing sound from cars as you go past, or if you stand on a platform where there's a high-speed train going past, you can hear that whooshing sound, which is the effect of air movement.
Now, if you go to the station, and I mean, this stands out in my memory because when I try to understand the announcements being made at a train station, it's almost impossible. Why are stations so bad for things like echoes?
Well, a lot of the big famous stations, Paddington and things like that, are just very, very vast spaces. And so you've got these reflections off the ceilings and the walls take a long time to reach you. And what literally happens is your ear decodes them as separate sound sources. I mean, if these reflections arrive early enough, your ear will just interpret them as all being from the same sound. I mean, that's the reason when we're in a normal room, we don't get confused by all this sound echoing around us. We kind of feel it's all coming from one source. But as soon as the sound's a delay because the room's too large, we then start hearing multiple sources. And once you get multiple sources, you're getting words running into each other. It's very difficult to hear announcements.
One of the other things that you made headlines for a few years ago, Trevor, was actually where this urban legend came from. I don't know, that ducks' quacks don't echo, but you proved that they do, didn't you?
Yeah, I did actually try and find the source of this myth, because it was been bugging me, but I haven't found out. If anyone listening knows, I'd love to know where it comes from. But yes, for some reason, we get these phrases that people recount as though they're science fact, even though they're wrong. And the phrase was, a duck's quack doesn't echo, and no one knows the reason why. And we got contacted by several different media organisations saying, is this true or isn't it? So we thought we ought to do something to dispel this myth, because, I mean, any sound echoes. It just may be in the case of a duck, it's rather difficult to hear.
And you actually proved that. What was her name, the duck that featured?
The duck who featured originally was Daisy, but unfortunately poor old Daisy's been eaten by a fox now.
So her echo certainly doesn't quack anymore, does it, so to speak?
No, we refilmed it for a channel, and we had to film it with daughter of Daisy, who was very temperamental and rather a vicious duck, I can tell you for free.
Now, we promised you another kitchen science, so here's Ben exploring how fat you would need to be in order to stop a bullet.
Hello, welcome to Kitchen Science. Today I've come over to Cambridge University's Cavendish Labs, and I'm here with Dr. David Williamson.
Hello.
And we wanted to find out how fat you'd need to be to stop a bullet. And it sounds pretty gruesome, but obviously we're not just going to shoot somebody. How are we going to test this out?
We're going to use gelatin, the type of gelatin that you might have in your kitchen. But rather than strawberry flavoured or raspberry flavoured, this is going to be plain gelatin, so it's transparent and clear.
So the plan is just to make up a load of jelly and then fire a bullet at it, is that right?
That's right. We have a plastic tube that's see-through. It's about 1/2 metre long, and we'll fill it up with gelatin, let that set, and we'll fire the bullet through the gelatin.
And what sort of gun are we using for this?
It's essentially like a large air rifle. It's got a barrel that's 3 metres long in length, and the air cylinder that we charge up with air is a couple of litres in capacity. So we'll charge that up, then we'll let the air go, and that'll push a bullet along the barrel and through our gelatin. The ball bearing that we'll use to simulate a bullet is 10mm steel.
What sort of speeds is this going to come out at?
I estimate it's going to come out around about 500 metres per second.
Wow.
That's approximately about 1,000 miles an hour, so that's really quite quickly.
That's really very fascinating. That's faster than the speed of sound.
Yeah, that's almost twice as fast as the speed of sound, which is 330 metres per second. So yeah, that's going quite quickly.
So why is it important that scientists know how materials like gelatin or human fat react to having a bullet thrown through them?
Well, I think there are 2 reasons. There's the case where someone might be shot and they survive, and you need to best understand what kind of wound that might have caused so you can treat it. And the other case, I guess, is, unfortunately, if you have a fatality, you might want to try and reconstruct the situation, infer what kind of weapon was used. That might give you leads to solving the case.
Well, we've got everything set up here, and so we have a tube of gelatin, a 3-metre-long barrel, our projectile is ready, but there's lots of big signs in here saying that we should wear ear protection. So I think it's probably best for our microphones if we do all of this from outside the room. Will that be okay?
I think that's the recommended procedure.
OK, well, let's go outside. OK, so we're outside now, and we're by a big metal box with 2 big switches. One says prime and one says fire.
So at the moment, we're just filling up the main cylinder with that compressed gas that's going to propel the bullet down our barrel.
OK, so are we ready to fire?
Yeah, sure. 3, 2, 1...
That was really loud, and we're the other side of a wall here, so I can't think how loud it must have been in there. We're just going to go in now, and we're going to see what has happened to our tube of gelatin. So, should we go in?
Yeah, let's go.
We're getting back towards the target chamber now, and I can see there's bits of gelatin all over this box. Not only has this bullet hit it, but it's totally shattered the tube. What's happened here?
Because we're outside the room, we couldn't actually see what happened. But even if it would have been inside the room, we still wouldn't have been able to see, because it happened so quickly, it's faster than the eye can discern. But fortunately, we were using one of our high-speed video cameras to record the process, and if we play that back in slow motion, we can see exactly what happened to our target.
So can we have a look now?
Yeah, sure. The first thing that we see is the air in front of the projectile that had been stored in the barrel has been pushed out of the way as the projectile went down the barrel. And that whoosh of air has deflected the gelatin at the entry side.
So it's just caused a bit of a distortion on the sort of the first edge of the gelatin, and that's just the air being pushed out of the barrel?
Yes, it's just the whoosh of the air has distorted the gelatin. The next thing that we see is the ball bearing has entered into the gelatin, and behind the ball bearing, a conical cavity has opened up. This is the ball bearing pushing the gelatin to the side as it goes forward. If you'd see a duck swimming in the river and the conical wake behind it, this is exactly the same thing. And material's been forced sideways. And we can actually see the force that's been applied has broken the Perspex tube that's containing the gelatin, and we can start to see cracks forming within the plastic.
I mean, that's amazing. You can actually see the whole thing shattering as it goes through. Do we know how fast it's going through there?
Initially, the ball bearing's travelling around 400 metres per second, but by the time it reaches the end of the tube, it's travelling at 200 metres per second.
So 36 centimetres of gelatin has halved the speed of this, but it still certainly hasn't stopped it.
Oh, certainly not. So we could make that rudimentary guess that maybe we'd have to double the length before we'd be able to bring the ball bearing to rest within the gelatin.
So this would be the equivalent, if we're talking about fat, of having 60 centimetres of fat all the way around you.
Yeah, that's right. You'd probably have to be around 2 metres wide before you'd be able to be bulletproof.
Well, that video is really cool. Can we take a copy?
Yeah, it's done in a digital format, so it'll work quite well for your website, I think.
Okay, excellent. We will put that online at www.thenakedscientist.com.
And you can find that online now. That was Ben with David Williamson at Cambridge University's Cavendish Labs, discovering that you would need to be unfeasibly fat in order to stop a bullet.
Sorting out the sparks from the quarks. The Naked Scientists. For more information, get online at nakedscientists.com.
This is the very best of The Naked Scientists with me, Ben Valsler, and Mira Senthilingam. We've just got time to squeeze in a few of your questions.
Let's have a quick chat to Richard. Hello, Richard.
Hello.
What's your question?
My question is, global warming, reference glaciers, reference if you put a glass of water, fill it up with ice cubes, when it melts it's exactly the same volume, hence the reason when glaciers melt there's absolutely no difference, so global warming, you've got it wrong.
Dave, what do you say to that?
You're right for ice floating on water. It shouldn't change the volume at all. But if you've got ice on Antarctica or on the Greenland ice sheet where it's on rock, nowhere near the sea, when that melts it's going to end up in the sea and increase the volume of the sea.
Yeah, that's absolutely right, because quite right, floating ice doesn't change the doesn't actually change the volume of water when it melts because it's displacing an equal amount to itself. But Greenland is a massive ice sheet, and there is tons and tons and tons of water locked up as ice on land on Greenland, which isn't affecting ocean levels. And in fact, the melting of ice on Greenland is raising the ocean depths by about 0.5 centimetre every single year at the moment. And if all that lot goes, within the next 100 years, we could see a 1 metre rise in sea level within the next 100 years. It's quite staggering, isn't it?
Well, to us in Essex, it'd be a serious problem.
It will be, actually. You could. I don't know where you are in Essex there, Richard, but you could be on sea.
I think we will be.
Here's another one from Adam Reynolds. He's 7 years old. He's in Minnesota in the USA. Sorry, I had to say it like that. I don't know why. Sorry, Adam. He says, I want to know why you get brain freeze when you drink an icy drink.
Oh, my goodness.
Do you have that?
I do, actually. Mostly with those sort of frappe coffee
Oh, you do
drinks.
dine out in posh places, don't you?
You know, I love those. You know, kind of
Frappuccino.
That sort of thing. And they're great on a hot day, but do make your nose and your head hurt. No, Chris, I don't know. Do tell me. Do you know why that is?
Well, I get this, and I was so intrigued because it happens to me. This horrible piercing headache right at the front when you eat something that's cold, obviously, or drink something that's cold. And so I started looking into it. No one actually knows precisely why it is, but theories are that this is a form of referred pain. And referred pain means you have damage or pain coming from somewhere in your body, but you feel it somewhere else. So, for instance, people who have a heart attack very often describe feeling pain in their neck or in their left arm, not actually where their heart is. So in the same way as that, you've got the nervous system fooling you into thinking the pain is coming from somewhere else. So what scientists think is that the nerves in the mouth that are very sensitive to cold temperature accidentally trigger the nerves supplying the front of your head into thinking that there's a painful stimulus coming from there, but actually it's coming from your mouth, but you're fooled into thinking that. Another possibility that people have put forward is that when you put very cold things into the mouth, there's a nerve reflex that's to do with regulating the temperature and blood flow through your face and head, because obviously warm blood keeps things warm. If you get too hot, lots of blood, you sweat, and then you cool down again. And it might be that when you put something very, very cold onto the nerves that signal this reflex, that it goes into overdrive and you get blood vessels temporarily opening up too much because they think your head's freezing cold. And in the same way as a migraine gives you that horrible throbbing headache, perhaps that's why you get that temporary, pulsatile, very, very throbbing, agonising pain right at the front of your head, and then it goes away when you warm up again. Who knows?
In extreme conditions, a headache caused by the cold could be the least of your worries.
Alan is in Orpington. Hi, Alan.
Yes.
You wanted to ask a question?
Yeah, I've been to the optician and I've got floaters in my eye, and so it gives the impression my eye is liquid. So how would, in extreme temperatures, does that stop it being frozen?
Well, actually, because your eyeball is contained within your head and your head's heated up to body temperature, it never actually freezes. So if you were dead, it would freeze. But since you're alive and radiating heat, it can't freeze.
And you were saying as well, David, quite interestingly, when you cry at the Antarctic or your eyes water, the tears don't freeze because they're salty.
Yeah, because they're very salty, and that lowers the freezing point of the liquid, and so therefore your tears don't freeze either. Well, they freeze pretty quickly once they get onto your cheeks.
Next, an explanation for one of the more annoying things that can happen to you in a bar.
I've got an email here from Rebecca in Wisconsin in the States, and she says, here in the States, when we're out at the bars and someone wants to be funny or annoying, they use the bottom of their beer bottle to tap the top of someone else's bottle, which makes the victim's beer fuzz up and overflow. Can you tell me the science behind this? Now, I have had this done to me, and it's very annoying, but I'm... Chris, any idea what that's about?
Well, it's similar to a question that we discussed not so long ago, Helen, isn't it? Where someone from Australia, I think, actually said, why is it when you go and get a can out of one of those can dispensers, and it seems to plummet to the bottom of this machine, and you open it, it just goes psst, and it doesn't explode all over you.
Whereas, thank you very much. I'm glad it doesn't. That would be...
Yeah, exactly. But why is that? And Dave and I were discussing it, and what we thought was, well, when the can falls, it tends to spin, and so it lands on its side with the liquid spinning in a circle inside the can rather than striking the top of the can. And because it's going round in a circle and the inside of the can is very smooth, what's probably likely to happen is that the fluid doesn't come into contact with any rough surfaces, so there's nowhere for the gas to nucleate or form tiny bubbles. So there's no way for it to actually form a big layer of foam, and therefore it doesn't want to explode.
I wonder if they figured that out first before they went and designed the machines, or is it just a happy coincidence that we aren't covering ourselves in fizzy drink every time we get a drink out of the machine?
They must have done, because it would have been a marketing disaster, wouldn't it? If you to get covered in a can of whatever every time you bought one. But to go back to the bottle, I think what could be going on here, of course, once the bottle is open, there's no pressure inside. So the gas that's dissolved in the beer, the carbon dioxide that makes it fizzy and frothy and refreshing, if that wants to obviously come out, which is why you've got the little bubbles forming, if you smash the top of the bottle hard with another bottle, it makes a shock wave. And I think that shockwave is enough to start some nucleation, in other words, a formation of some tiny bubbles inside the drink. And once you've got one bubble formed, it forms a site for more to form on, so then the whole thing sort of feeds back on itself. And these beer bottles have a very narrow neck, so as soon as you make a little bit of foam, the foam very quickly blocks the neck, and then the whole thing has nowhere to expand, and so it just pushes everything out in a massive, great volcano, if you like. I reckon that's what's going on.
OK, Rebecca, well, I hope that helps to answer your question.
And finally, Dave and Anna go all squeaky to answer a common question.
The question we're going to try and answer is...
why your voice sounds funny on helium.
So one of the answers people usually give for this is that the helium makes your vocal cords tighter unless you get a higher sound. But that's not actually the case, is it?
No, your vocal cords are doing exactly the same thing in helium and in normal air.
OK, so tell me, what's actually happening when we speak and make a sound?
Well, your vocal cords make all sorts of different frequencies down in your throat. And your throat and your mouth select some frequencies and make those much stronger. You can see why that is with this roasting tray down here.
So now what we've got here, we've got a roasting tray on Dave's kitchen table here, full of about an inch of water. What are you going to do with it?
Basically, I'm just going to wobble it. I can wobble it at all sorts of different speeds, at different frequencies. At most frequencies, not a lot interesting happens. It just gets a bit wavy. Now, if, on the other hand, I pick this frequency... every time I wobble my hand, I'm strengthening that wave, and it's reflecting off the other side, and it's coming back, and I strengthen it again and again and again, so it's getting bigger and bigger and bigger.
What we can see here is Dave's kind of whooshing the tray backwards and forwards, and there's just one big wave that goes to the other side, hits the side, comes back, and then Dave's ready to push the tray again to sort of throw the wave back again. So what now?
Well, I could wobble this tray at any frequency, but it's only this frequency and actually double it and triple it and a whole series like that, which will get amplified like this.
OK, so now we've seen this water going backwards and forwards. You know, what is that and what's that got to do with our voice?
Well, this effect is called resonance, this strengthening of certain frequencies. Now, as I was saying earlier, your vocal cords make a whole series of frequencies. And as the sound waves go backwards and forwards, well, they'll reflect off your mouth and will go backwards and forwards up and down your throat and mouth.
A bit like we just saw with the waves going backwards and forwards in the tray.
Yeah, exactly. So they'll tend to strengthen some frequencies over others. Now, waves move much faster in helium than they do in air. So if it was in my tray, it would be like the wave going backwards and forwards much quicker. So in order to get this amplification effect, I'd have to wobble the tray faster. So higher frequencies would get picked out.
So really what's happening is sound travels much faster through helium than it does through air. So that means that when all those frequencies leave your vocal cords, they go through the vocal tract and then get reflected back and bounced around in your mouth much quicker. And like the waves in the tray, when the waves are moving quicker, the frequencies that you're picking out are also much higher. And a higher frequency equals a higher pitch.
So when I speak on helium, the higher pitches are amplified so it sounds silly.
OK, so Dave, of course, the last word obviously has to be with you.
Well, I hope that makes sense to everyone, and everyone has a great evening.
Dave Ansell and Anna Lacey taking the risks so you don't have to. Unfortunately, that's all we have time for, and next week Chris and the team will be back from their holidays, and they'll tackle more of your tricky science questions. So if you've got a question you're just dying to know the answer to, get them into chris@thenakedscientists.com.
And don't forget our question of the week, looking into why old broken bones can sometimes predict the weather. If you know why, or if you have your own personal barometer, let us know by emailing questionoftheweek@thenakedscientists.com.
And while you're online, why not pay a visit to our science discussion community found on our web forum at thenakedscientists.com/forum.
We hope you've enjoyed looking back over the best bits of the series. Don't forget to tune in next week for more of The Naked Scientists. That's it from me, Mira Senthilingam.
And from me, Ben Valsler.
Goodbye.